Hello wonderful person, this is Anton, and today we're going to be discussing some of the more recent updates in regards to the famous NASA's DART mission. The mission that even has this really cool animation when you search for it on Google. And that's because this was one of the most important missions in NASA's history. The actual physical tests of the concept referred to as asteroid redirection, or essentially, as the name implies, trying to redirect an asteroid that in theory could be on a collision course with planet Earth. But in this case, NASA chose a very distant asteroid, the one that's unlikely to collide with the planet ever. This was the Didymos system containing two separate objects, with the NASA's DART probe colliding with the smaller moon referred to as Dimorphos. We've discussed all of this back in September of 2022, and you can learn more about this in one of the videos in the description. And as you might remember from those older videos, or as you might have heard somewhere else, the mission was a complete success. It accomplished its main goal of changing the orbit through this relatively simple collision. But while the initial results were hailed a success, basically shifting the orbit by approximately 32 to 33 minutes, recent studies have also revealed that the physics of this impact were way more complex than we ever imagined, which is what most of the studies from the last few months essentially reported. And so, as it turns out, we didn't just nudge this rock, and instead we may have permanently reshaped it and also sent it in a kind of a chaotic tumble that was completely unexpected, which suggests that our understanding of debris in outer space, or the way that it seems to behave, seems to be completely off. But I guess before we discuss some of the major discoveries, let's also discuss the basics, in case you've never heard of this mission before. And so let's discuss what we know for certain. First, the impactor. This was a 610 kilogram kinetic impactor that hit Dimorphos at 6.2 kilometers per second. But the reason this impact was so effective was not just the velocity or the weight, it was actually the recoil effect from millions and millions of kilograms of debris, or specifically ejecta, that was then blasted into outer space, as you see right here. These are the actual observations right after the impact. Now, in order to measure the momentum enhancement, or by how much this rock was moved, scientists usually use the value referred to as beta. And for DART, this factor was about 3.6, basically meaning that the ejecta contributed 3.6 times more than the actual impact, essentially kind of acting like a little space engine that changed the velocity of the rock even more. But even more profound in this case was the fact that this also altered the entire binary system and even the orbit around the Sun, which basically marks this the first time in history that human action actually changed the path of a natural celestial body through the entire solar system. Or just to rephrase this, even though the original plan was to just change the orbit of the moon of the asteroid, in this case, because of this initial impact, it actually changed the orbit of both, with the system's 2-year journey around the Sun slowing down by approximately 11.7 microns per second. Now, this is obviously a somewhat tiny amount, but it does prove to us that we can now physically push the asteroids with just one single satellite. But some of the recent analysis also shows us that the impact did so much more. For example, first of all, it seems to have changed the shape. Before the impact, Dimorphos was most likely oblate in shape. Basically, you can see it right here, and it was kind of shaped like a hamburger. But after the impact, it's now prolate. It seems to resemble more a football and seems to have become elongated. And the discovery here was kind of shocking. Scientists did not expect such a huge change in shape just because of one single impact. And this change of shape suggests only one thing. It basically confirms that quite a lot of different asteroids are not physical rocks, but they're more like a collection of rubble. And this change in shape suggests that Dimorphos is a rubble pile, just like so many other asteroids we visited. So basically, it's not just a single rock. Instead, this is a collection of rocks held together by gravity, and possibly some kind of an electrostatic force as well. And because it's so loose, the impact did not just leave a crater, but instead completely deformed the entire object. And so these previous images that imagined this object to be this way could not have imagined that it's going to result in something like this. And by the way, here is actually one of the last pictures physically captured from this probe before the collision. And so here, as you can see, this is basically just a bunch of rocks held together. But because this was a rubble that's now basically recombined, it may also now be tumbling. So basically it's wobbling back and forth, and very likely rotating in a kind of a chaotic way. And that actually might complicate some things for the future HERA mission. The follow-up observation mission that's going to be arriving here in November of 2026 in order to conduct additional observations. And well, that's going to be happening in just a few months from when I'm making this video, so it's actually going to be really exciting to find out what this probe discovers. But if this asteroid is tumbling, it might actually make the landing or even performing a close-up survey much more difficult and even more dangerous. This is something that nobody anticipated when HERA was officially launched. But that was just one of the first discoveries. Additionally, there was something else. And specifically this was based on the observations from the ground-based telescopes that noticed that after the initial 32-minute orbital shift, the orbital period dropped by an additional 30 seconds. And initially researchers believed that this was possibly the result of all of the debris escaping from the system and eventually carrying away some of the angular momentum, causing the orbit to shrink further. But in a much more recent study by researchers Harrison Agrusa and Camille Chatanet, whose research you can find along with other studies in the description below, essentially ruled this out. And so based on various N-body simulations, they discovered that if the material escaping was indeed changing the orbit, it actually should have increased the period, not decreased it. And so instead they propose that it was actually due to the rotation-induced reshaping. Or basically because the change of the object shaped over time, this also potentially changed the orbital period. Alternatively, they proposed that this was maybe the result of massive landslides that were triggered on the surface, possibly hours or days after the collision. Which once again makes predicting things when it comes to asteroid collision just a little bit more challenging, because nobody could anticipate any of these effects or any of these changes. But here we also learned just a little bit more about the debris itself. This was based on different observations from the small Italian CubeSat Lilia cube that tracked over 100 different boulders that were blown away from the surface. And these boulders were not scattered randomly and instead seemed to be clustered in two distinct groups, which essentially suggests that there seems to be something unknown going on here, and nobody can explain why these boulders seem to have clustered in such a way. Although here we also know that at least two of these boulders, you can see them labeled in this image, were actually independently struck by the solar panels from this probe. And this surprisingly happened just milliseconds before the collision of the main spacecraft. And while here, based on some of the calculations, some of this dispersal and the fragmentation and the scattering could have been because of the shape of the probe and because of how it collided with the object. And a lot of the momentum in this case was actually directed toward the south of the object, which might have tilted Dimorphos's entire orbital plane by approximately 1 degree. And while that could maybe explain some of the observations, including the orbital shifts and the change in shape. But obviously, at least for now, this is just one such study trying to figure out why this happened. But the most important conclusion from this study essentially highlights that we cannot simply rely on a kind of a hit and hope approach when redirecting these objects. Because in this case, the internal structure and the surface rubble, including even individual rocks, seem to dictate how much and in what direction the asteroid will shift to. And so, for example, if we hit a different part of the object, and if the space probe interacted with different rocks, everything could have been very different. And so this is not some kind of a simple game of billiards, and instead the presence of large boulders on the surface seemed to wildly alter the outcome. Which basically means initial reconnaissance and complex modeling has to be done before any future additional collision. But then we have additional discoveries from this most recent study. This is from March of 2026. Here, based on some of the experiments on the planet involving marble experiments simulating cosmic snowballs, this recent study discovered another unusual evidence for what seems to be unusual fan-shaped streaks on Dimorphos. This was actually visible in some of the last images before the probe hit the surface. And well, it turns out that once you remove all the shadows, this is kind of what you get. And these are deposits of dust and rock that seem to have been naturally drifting from the larger object, Didymos, and eventually being deposited on the surface of the smaller moon. Although intriguingly here, this material travels very slowly, approximately 30 centimeters per second or 1 foot per second. With all of this very likely happening for an extremely long time. And while surprisingly, this proves a really important concept. This is the first ever direct visual evidence of the effect known as YORP. This is basically when sunlight causes asteroids to spin just a little bit faster until some of the material from the surface starts to fly off at the equator and then possibly land somewhere else, like for example, its moon. This image right here from University of Arizona basically summarizes how this effect works. And so, in essence, because the sun causes many asteroids to spin faster and faster, pretty much all of them eventually start losing material from the surface, and in this case, it seems to deposit on the partner, forming this very strange fan shape on the surface. And here, interestingly, the moon, if it spins fast enough, will actually do the same. It's going to throw off some of the material from its equator, and that material is probably going to land on the larger object. And so in essence, this is a direct proof that a lot of asteroids seem to share their own material that eventually gets deposited on their surface. But because this is a low velocity impact, here researchers describe them as cosmic snowballs, very slow moving impacts of dust and rock, and not high-speed collisions. Which is basically what they've tried to simulate right here. This is kind of what it might resemble. And this is extremely likely to happen in most of these binary systems, which represent approximately 15% of all asteroid systems around us. And so by understanding how these rubble pile binary asteroids exchange materials and how they respond to sunlight may help us predict their behavior and their structural integrity much better. Once again, the ESA's HERA mission is hopefully going to provide even more evidence or more discoveries in regards to this, sometimes before the end of 2026. But what about all of these ejected rocks? Where are they going to end up eventually, and is there anything we can learn from them? Well, it turns out that this human-made meteor shower, that's now referred to as dimorphids, actually does have a chance to one day land on Earth, with simulations indicating that some of these faster-moving particles possibly even coming here within the next 7 years. And so essentially by 2029-2030, we might actually get some of the first particles re-entering our own atmosphere and basically creating some of the first man-made meteor shower. Now, just to clarify, there is absolutely no risk to Earth from this, but just the idea that this is a meteor shower created by humans is kind of mind-blowing. But because most of these particles are going to be pretty small, very likely just a few inches or less than 10 centimeters in size, we're unlikely to capture any of them. But for astronomers, this is still important because it essentially shows us how a lot of material seems to move across the solar system, which will hopefully help astronomers improve some of the models for planetary defense, and once again figure out how to better redirect these rubble pile asteroids just a little bit better. And last but not least, we also have some additional predictions or additional models in regards to potential future redirect mission, or essentially how to make this just a little bit more effective. And so here in the additional study, researchers confirmed that by having a large impactor, mostly hitting some kind of a rounded surface, the overall deflection seems to be reduced by approximately 56%, at least compared to a flat surface. And so here the solution is to actually use multiple smaller impactors, which will maximize the momentum transfer and also provide a kind of a tactical flexibility and maybe even cost much less. So basically, instead of having one single probe that weighs approximately half a ton, it might be better to just have 10 of them weighing just a few kilograms and resembling a typical CubeSat. And because most of the momentum in this case seems to come from the ejecta, by colliding these satellites in just the right way, it might become possible to maximize the ejecta and thus maximize the momentum transfer. And so here at least one study actually makes this even more efficient by proposing several smaller probes that possibly hit in different places. And so in the end, this mission was absolutely incredible. It definitely showed us that asteroids in general seem to be very dynamic and change all the time, and are definitely not these static rocks we imagined them to be previously. It also taught us that a lot of these kinetic impactors result in some very complex situations and seem to produce effects we never even knew existed. But I guess most importantly, all of this showed us that redirecting asteroids is definitely possible, and actually using some really simple missions that basically just collide a bunch of small satellites and create massive amounts of ejecta. But the thing is, before the end of this year, we're going to have even more information because of the ESA's HERA mission. And so once it reaches the system and basically investigates this crime scene, we'll hopefully be able to answer some additional questions and understand all of this just a little bit better. On that note, once we have some updates, we'll discuss this again. But until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads, and can DM me directly or by joining channel membership that grants you early access. You can also support this channel by buying the wonderful person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.